announcement. I'm not in the Department of Physics. I'm in the Department of Earth, Ocean, and Atmospheric Sciences here at UBC. My work is mostly in planetary geophysics, some in terrestrial geophysics, more recently looking at other planets, mostly at inner solar system bodies. And a lot of my research recently has been on the magnetic fields of some of the inner solar system bodies, specifically Mercury. So I was working a lot recently with data from the MESSENGER mission. I was a participating scientist on that mission, and a little bit in the past in general geophysics on Venus and on Mars, some work on the moon with some of the Apollo observations of seismic data, and some of the Apollo return samples, actually looking at the record of the lunar magnetic field. But today I thought I'd talk a little bit about Mars. This is work that's very much in progress, and in the talk I'm going to try to pitch it for people who don't necessarily think about Mars every day and also don't think about magnetic fields every day. So please just chime in if you have questions along the way. I'm happy to take interruptions. And the work that I'm going to talk about is mostly work that I've been doing with Anna Mittelholz, who's a PhD student here in my group. But some of the things that I'll mention are kind of problems that I've thought about or worked a little bit on for many years now, kind of dabbling in various aspects of trying to understand the record of crustal magnetization on Mars. And a lot of that work has been in collaboration with Roger Phillips, who is at Southwest Research Institute, and Kristen Lawrence, who's a former PhD student with me, and then Rob Lillis, who's a space physicist who's involved with the MAVEN mission. So I thought what I'd do is just give a little bit, well, we'd have a little bit of discussion, hopefully, about magnetic fields that are observed in planetary environments, what kinds of sources there are for those fields and what they mean. And then I'm really going to talk about two topics, Mars's crustal magnetic field, and a lot of that will be just some review of what people have found previously, but really trying to point the way to what I think will be some avenues for research with some of the MAVEN data, some preliminary work that we've been doing here on that, and then looking at the magnetic field environment around the planet Mars. So not just magnetic fields that are generated inside the planet, but ones that are external to the planet, and really looking at those with a view towards being able to do some interesting things that I'll talk about with the InSight mission to Mars, which will put a lander on the surface of Mars to measure seismicity, heat flow, and the surface magnetic field. So I wanted to start actually with thinking about why we care about magnetic fields, and I was hoping maybe those of you, particularly in the room there at York, could chime in. You can unmute. And what I wanted to do to start with was just get some ideas from you guys about what are the different sources for magnetic fields that can be present in a planetary environment. So where do those magnetic fields come from? They can come from a variety of different sources. So that would be the first question. And then we'll think about what kinds of things do those magnetic fields from different sources actually tell us about the planet or about its environment. So maybe those of you guys who are in the room at York, and then anybody else who's online who wants to chime in, what are some different sources for magnetic fields that we might observe if we were to be able to measure the magnetic field at the surface of a planet or just above the surface of a planet with a satellite, say?
I expect the dynamo would contribute to the magnetic field.
Okay, so one would be a dynamo. One might be a dynamo source. What do you mean by a dynamo source in
Uh,
this context?
like flows under the surface, like the core and the mantle.
Yep, so possibly magnetic fields that are generated deep in the planet. Usually for terrestrial planets, inner solar system planets, this would be in the liquid part of a fluid, the liquid part of an iron core. And so magnetic fields that are generated by the motion of that fluid that leads to electric currents. So that can generate a magnetic field. If we observe that magnetic field at the surface, is it typically just present in one region, or is it global, or what might we be able to say about it? Maybe somebody else. Is it just observed in one region typically?
Global?
Yeah, no. So it would typically be a global field. And at the Earth, what's the structure of that global field? What does it look like? If you just, yeah, it looks like a dipole field, right? So we can have sources of magnetic fields from the planet's core. So we call that a dynamo field. It usually results in a large-scale global field at the Earth that looks like a dipole field. It does at some of the other planets too. What would be might be some other sources, either from inside the planet or above the planet's surface?
The sun's magnetic fields at the top of the atmosphere might have some.
Could you speak up a bit?
I don't know where the microphone is.
It's in this.
The sun's magnetic field, you get interaction between the planets one and the sun.
Yep. So the sun's magnetic field. So the sun generates a magnetic field, right, which is carried away from the sun by the solar wind and is then referred to as the interplanetary magnetic field. So that's present around all planets in some way that we'll talk about. So the interplanetary magnetic field. Anything else?
Get a large deposit of some kind of metal or ore, like iron. I guess that might have its own local magnetic field. I'm not a geologist.
Say that again.
Some kind of large deposit of iron ore might have its
Yep. Yep. Yeah. So rocks with magnetic minerals in them can generate magnetic fields. So magnetized rocks, and on the Earth, you're absolutely right. So on the Earth, those are particularly obvious in regions where there are big kind of iron ore deposits. So strongly magnetic rocks. So rocks can be magnetized in a variety of different kinds of ways, and we'll talk about that just a little bit here. So magnetized rocks. Anything else? So there are some other sources for fields that are generated above the surface of the planet, and we'll talk about those, and maybe one other source of magnetic fields that are generated inside the planet. So those are some of the major, the ones that you guys have mentioned now are some of the major sources of magnetic fields that might be present in a planetary environment. So if we look at those, so this slide basically shows some of the sources for magnetic fields that might be generated internal to a planet. So you guys mentioned ones that are generated by a core dynamo. Those are typically global in scale. Why are they important? Well, they're important. The first order thing that's important about them is if you see a global scale planetary magnetic field for a terrestrial planet, then you know that at least part of the interior has to be fluid and generating that magnetic field. So it actually tells you something about the interior structure of the core. It tells you at least part of the core has to be fluid. So in fact, the presence of a global magnetic field is a very important diagnostic of interior structure. And then whether or not the fluid in that core can convect sufficiently vigorously to generate a global scale magnetic field depends, among other things, on buoyancy sources in the core. Essentially, how quickly is that core cooling? How quickly can you convect the material? And then also on whether or not there are light elements present that might result in convection in the core. So the presence of a magnetic field today tells you something about interior structure, but also indirectly something about interior thermal state. And the presence of a global field in the past tells you something about essentially the thermal evolution of a planet. So it's a very important, it's indirect, but it's a very, very important kind of first order diagnostic of planetary structure and planetary evolution through time. Crustal magnetization, if that's present, it tells you, or crustal magnetic fields, those are typically regional in scale. So the suggestion that was mentioned is if you have iron ore deposits, so these would be regional in scale. So crustal magnetic fields vary depending on where you are. If you're in a region that has very weakly magnetic sediments on the Earth, then you see very weak magnetic fields. If you have stronger or different iron mineralogies, so in this figure here, a particular difference is between the continents and the oceans on the Earth. Much stronger, smaller scale magnetic fields, smaller scale compared with the dynamo field that you see over the continents, and those are much stronger compared with the ones in the oceans. And the fact that you have crustal magnetic fields tells you that those rocks are magnetized. So indirectly, it tells you something about the mineralogy. It tells you they have to have some kind of iron mineralogy. And it tells you that they have to have sat in a magnetic field, either today or in the past, to become magnetized. So indirectly, they're a probe of the planet's magnetic field history. And then the third way that magnetic fields can be generated inside a planet is by what we call induction. If a planet sits in an environment where exterior to the planet there are time-varying magnetic fields, those can in turn induce electric currents in the interior of the planet. And those currents will result in secondary magnetic fields that, if they're strong enough, you can measure them, perhaps at the surface, perhaps at spacecraft altitude. And so if you can measure those, the strength of those secondary fields tells you something about the interior electrical conductivity structure. And in particular, its electrical conductivity structure is dependent on temperature of the rocks and on their water content. So this will be actually very important diagnostic of water content, possibly for thinking about the interior of Mars. So those are three ways that you can, three sources for magnetic fields, and they tell us different things about the interior structure of the planet. When we think about the environment around the planet itself, so this is an example for the Earth, there's the interplanetary magnetic field, this was mentioned, carried by the solar wind towards the planet. And in the case of a planet with a global dipole field like that of the Earth, the planet itself and the magnetic field of the planet are basically together an obstacle to the solar wind. And so the solar wind is slowed at this shock here called the bow shock and mostly diverted around the planet. And the region where the planet's magnetic field is, within which the planet's magnetic field is confined, is bounded by this region here called the magnetopause. And on the surface of the magnetopause, there are electric currents. They're the currents that essentially confine the planet's magnetic field and exclude the interplanetary field to first order. And so in the vicinity of the planet itself, if you were to fly a spacecraft above the surface of the Earth here, you will measure not just the Earth's magnetic field, but also a contribution that is produced by electric currents generated exterior to the planet. And those result just from the interaction of the planet and its magnetic field with the solar wind. Even if the planet doesn't have a magnetic field, there's something a little bit like a magnetospheric.